Okay. So I'm going to give a definition. So let theta be a linear operator on a vector space. Okay, and it can be, it's possibly infinite dimensional. Okay, we're going to define to be equal to the sum from j is equal to 1 up to infinity of lambda j to the negative s. Here, so these guys at lambda 2 and so on. So these are the eigenvalues of lambda, of theta. And we're going to denote the eigenvalues, so this is going to be the point spectrum of this operator theta. We're also going to assume that theta, all these are going to appear with multiplicity 1. Okay? So, definition. So, this definition, let me just say this. So, a regularized product, or a zeta regularized product, is just this formula. So I'm going to define a product of an infinite number of things. So it's going to be defined to be the exponential of negative of zeta theta prime at 0. And so this is done by analytic continuation. In general, analytic continuation. Here, I guess you don't need these to be associated to an operator, but I mean, you could just take like a sequence of complex numbers and this will work. All right, so let me give you an example. So, if we just have a finite number of these, so let's say they're for some other operator, A. Okay, then say A prime of S is equal to, so we just have this, you take derivatives of these powers from calculus, okay, and this tells us that we have the following. So when we plug in 0, and so when we do the regularized product for a finite number of things, we're going to find that this is, okay, so we take the definition, we're going to find that, so minus log j. So we have x to logs. We find that this is just the product. Okay, so this is some generalization of the product. So we recover the other things. So if we have an unbounded operator, then so if we have an operator on an infinite dimensional space with eigenvalues, say simple eigenvalues, we define this regularized determinant to be this regularized product of the eigenvalues. So this is the regularized determinant.